This tutorial discusses electron configurations and the abbreviated configurations. We're going to use something called the Fblock principle, which is German for the words build up. This is a pattern of orbital filling lower energy first. First, write the list of energy levels and orbitals. So in the first energy level, we have the s orbital, and it can hold 2 electrons. On the second energy level, we have the s orbital, which can hold 2 electrons, and we also have the p orbital that can hold 6 electrons. On the third energy level, we have s, p, and we also have d that can hold 10. On the fourth energy, we have s, p, and d, but we also have f. And we're just going to keep going with these until we get to 7. And one more. From here, we're going to draw diagonal lines to identify how the electrons are going to be added. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and we're going to just keep going down. 4d6, 5p6, 6s2. We're going to keep going. Alright, now when we do electron configurations, we're going to be adding up the small numbers here until we get to the number of electrons we need. Alright, so the Fblock chart, this is a clearer example. This one does not have the electrons written in, which is actually really important because that's going to tell you how many more electrons you need. I'm going to write these in real fast. And what you're going to do is you're going to follow the counting of electrons down diagonally until you get to the amount that you need. Alright, so let's start with sodium. 2, 2, 6, 2, 6, 2, 10, 6, 2. Alright, we know that the atomic number is 11. So that means we have 11 protons. If the atom is neutral, that means we also have 11 electrons. And so that's how many we're going to try to get to. So 1s2, 2s2, 2p6, that's 2 plus 2 plus 6 is 10 electrons. We need one more. So 1s2, 2s2, 2p6, 3s2 is next. However, we have 10, we only need one more, so it's going to be 3s1. Alright, so it has an atomic number of 11, so if it's neutral, it has 11 electrons. Electron configuration we just determined by using the chart. This is showing as the energy goes up, it fills from the bottom up. 3s1 only has 1 electron. There's another way to identify this rather than write all of that out. If we look at neon, neon is right here. We can only do this with the noble gases. What you're going to say is that sodium is all the electrons that neon has, because it's the one right in front of it, plus one more. So neon encompasses all of this. So this is called a noble gas notation. Neon is in brackets, and then we add 3s1 to it. The first two energy levels are filled, or the neon core. And so this is the neon here represents this. And when you're looking at the periodic table, you can do this with any element. For instance, let's look at gallium. Gallium is 31. Go to the left and look at the previous noble gas. It's argon. So gallium is going to be everything that argon has plus whatever it takes to add up to 31. So if we were to start at 3p6, because that's where argon is, here's 3p6, 4s2, 3d10, 4p, to get up to 4p1, to have that configuration. So the inner core electrons are the filled shells. The valence electrons are the electrons occupying the outermost energy level. These are the electrons that are participating in the bonding. They're the ones that lose, they're the one that goes away and get lost to make cations, and they're the ones that are being gained to make anions. So here's silicon. It's the neon gas formation, electron configuration, plus 3s2, 3p2. Let's talk about this area down here that we haven't really spent a whole lot of time talking about. Those are the transition metals. Their valence shell contains the d electrons. The d electrons first appear in the fourth period. However, when we're writing it out, we start it with 3d. This is because, once again, the Fblock principle, if we come here, that's messy now. If we come here, even though we're starting in 4, we go 3p6, 4s2, 3d10. Because we entered the 4s2 before they enter the 3d10, they've shifted it down to represent that. So these are the 4s1s, and then 3d1. So the 3d electrons are in the fourth period, the 4d electrons are in the fifth, 5d are in the sixth, and 6d are in the seventh. Now the Fblock is the inner transition metals. They're right here. They start at the 6th row, because remember, these have been taken out because there's not enough room. The 4f electrons are in the 6th period, and the 5f electrons are in the 7th period, and that's for the same reason of the Fblock chart. However, not all elements are as easy to predict. The actual electron configuration of some elements, specifically those found in the transition and inner transition metal section, have an arrangement that is not predicted. The NS, where N is equal to 4, 5, or 6, has a lower energy than the N minus L d orbitals, where N is 3, 4, and 5. When empty, and therefore electrons enter the NS orbital before the d orbitals. Example is 4s fills before the 3d orbital. The energy difference between s and d orbitals are not large. Also, as the d orbitals are filled, their energy level becomes lower than that of the s orbitals. And this creates an issue called sublevel splitting. It's trying to create the lowest energy possible for that atom. And that's why it's not always easy to predict. The s orbital only partially fills before electrons start entering the d orbitals. Or it doesn't fit at all, and all electrons go straight to the d orbital. Here are some examples. Chromium, we predict it with the Fblock principle to have 4s2, 3d4. But in reality, when we do experimentation, we find that the electrons try to expand out. So let's think about this logically. We have 4s with only one orbital, and then we have d, which has 5 options, 5 configuration. And we say that there's 4. However, what happens is one of these electrons gets promoted up to be 4s 3d5, because that way all these electrons are in their own subshell and they're a lot more relaxed. Copper, 4s2 3d10, the 4s once again gets promoted to 3d10 from 3d9 to 3d10 because it's a more relaxed configuration. If you look at molybdenum, it's doing the exact same thing chromium did. So basically what's happening is these turn out to be a more stable configuration than what it was to be predicted. And that is how you do the noble gas configurations for electron configurations.